Any questions before I start that? That also said that the RMS value of the voltage from the power source, so the power source RMS was 120 volts, which had us come up with the power source max, which I labeled as epsilons of 0. 169.7 volts. I just want to point out that epsilons of 0 is something we've been using for permittivity of space, free space, and this epsilon sub 0 is not the same epsilon sub 0. This is an epsilon for EMF, and sub 0, sometimes I'll do sub m, but habit has me putting this 0 there for it. It's the amplitude of the voltage coming from the power supply. And let's see, also had that the frequency was 60 hertz, which had us come up with the angular frequency of 377 radians per second. And ultimately, we had the impedance in 1,199.8 ohms. And our phasor, let's see, so it's a series circuit right there. Current is going to be the same, so I had the current from the power supply is the current from across the resistor, which is the current across the capacitor. VC was along the same line as, V sub R is along the same line as I sub R, because the voltage phasor of the resistor is in phase with the current phasor. So it'd be VR. And I know that for the capacitor, the current leads the voltage, or the EMF of the capacitor, so the capacitor is down here. Because there's the current for the capacitor, and so I come back 90 degrees, or pi over 2. And the voltage across the resistor plus the voltage across the capacitor is the voltage of the power supply. And so there's the phasor for the power supply. We also had that. Now, whenever you're doing phase shifts, you have to establish what 0 is, and that's what we had done early on, is that the voltage from the power supply, and this is a lowercase v, when I put the little tag right there, just to differentiate it from my uppercase v's, which is just straight up 2 line segments. So this was 169.7 volts cosine of omega t, was 377 radians per second time, and we are establishing that as when time is equal to 0, the power supply is at its maximum, and everything else is based upon that. So when we came up with the formula for the current, from the power supply, or actually it's the current from pretty much all of them, because since it's the same current through a series circuit, we had 0.14 amperes times the cosine of 377 radians per second times the period times time plus, and that is where we left off last Tuesday. I need to figure out what is the difference in the angle between my voltage from the power supply and my current. So I need to find this angle I just marked in purple, which I will cleverly label phi. Oh, I have a right triangle there. If I sort of pull that right triangle out, the length of this side right here is VR. The length of this side right here is VC. There's my phi. There's my hypotenuse. But I'm trying to find phi here, and I know these two things, so it seems like tangent's in order. The tangent of phi is equal to VC over VR. Now, at this red hot second, I don't know what they are, but that doesn't matter. Because I know that when I'm dealing with the magnitudes here, which I am, the Ohm's law equivalence applies. So this is equal to the current times the capacitive reactance divided by the current times the resistance. I could throw an extra step in there and label this I sub C and I sub R, but it's the same current for this particular problem. Currents cancel out, and I'm left with my capacitive reactance divided by my resistance, which was 663 ohms, divided by 1,000 ohms. And just as a quick review, the 663 we found last time, the capacitive reactance, the formula is 1 over omega times C, and there's my omega, there's my C. So just plug and jog. So phi is the arctan of 0.663, which is
.54.
And you're missing something.
Degrees.
Yeah. And it does become critical here because this is in radians per second, and we got to be careful about, if we're going to put degrees here, then we're dealing with mixed units. And it's resolvable, but it'd be nice to be clear what we're doing. So if that's 33.54 degrees, well, we can now figure out what this angle is, because I know that's a right angle. So this has to be the complement. So 56.46 degrees. Assuming that's correct. And because we're cool, what are these angles in degrees? Or sorry, in radians?
0.585.
And the other one?
.55.
This is 1.55?
Yeah.
No. No way, that's 1.5. 56.46 degrees.
You're taking the arctan of it?
No, we're finding it in
What is it in radians?
8.985.
That makes more sense. Because 1 radian is about 57 degrees, so I do 1.5 would be it. So if this is 0 right here, because again, I've got these 1, 2, 3, 4, 5, I have these 6 phasors, just 3 of them happen to be identical. I have 6 phasors here, and they're all rotating around this pivot point at an angular speed of omega. This, my current here, is ahead of my power supply voltage by that angle right there. And so, into this blank. We put in plus 0.585. I don't have to write radians. So that's the current from the power supply, which is the current from across the resistor, which is the current power supply, which is the current with the capacitor, across the capacitor. Now we can do our voltages. We'd already figured out capital I at 0.14. So I know my maximum value of the voltage across my capacitor is 0.14 amperes times my capacitive reactance of 663 ohms. Something?
92.82.
Units?
Ohms. Volts.
What'd you say?
Volts.
I think I heard you say volts.
Volts.
Volts. We're finding the maximum voltage across the capacitor.
Okay.
Or ampere ohms if you're desperate. So VC is 92.82 volts times the cosine of 377 radians per second times time. And now the phase shift for the capacitor voltage, voltage of the capacitor, is this angle right here. It's behind it because, again, these things are rotating counterclockwise because somebody along the line decided that was proper. I'm guessing the person who did not invent the clock. So they're going around like this. This is in front, so minus 0.985. And then voltage across the resistor. Well, there's my maximum right there, I times R, so VR is 0.14 amperes times 1,000. I think I can do this one in my head. 140 volts, cosine 377 radians per second times time, plus 0.585. Because the voltage across the resistor, that phaser's sitting right on top of the current one. So I have my 6 equations, where 3 of them happen to be identical. So typically on a problem like this, there's going to be a voltage equation and a current equation for each component. I got 3 components, so I got 6 equations. Conveniently, there's a lot of overlap. That will change before the night is done. All right, questions at this point. We're going to do a quick check just to see if this makes any sense at all. And as with all checking, it's that double-edged sword. If it comes out okay, then you should feel good. If it doesn't come out okay, then the question is how much time you want to spend trying to find the problem. And for me, it depends upon my mood at the moment. All right, let's do a quick check. We did our voltage, maximum voltage across the resistor is equal to I times R. Maximum voltage across the capacitor is equal to I times X sub C, where X sub C is 1 over omega times C. Not in this problem, but in a future problem, V sub L is equal to I times X sub L, the capacitive reactance, where X sub L is equal to omega times the inductance. So the Ohm's law equivalent, and then we also have epsilon sub 0 is equal to I times, I guess, the power supply times the impedance. That's I sub L, I sub C, I sub R. So these formulas are always gonna be true as we work through this. But Kirchhoff's rules apply to the instantaneous values. If I go from this point to this point, either path, I should have the exact same voltage, so my voltage across my power supply should be the same as the sum of my voltages across here. And those are instantaneous values. So let's pick a time of
3.
we want to go real, I mean, think about this. If you have these phasers are spinning around 377 times radians per second, which ended up being, they're spinning around 60 times a second. So let's go for a tiny number. The reason and if possible 2 or 3 would work perfectly. I did that the other day and the numbers came out really close to the maximum values. It ended up being a disappointing answer. So I'm feeling burned by it.
Is that 0.5 or 0.05?
0.05. Oh, let's throw another 0 in there, 0.005. And so it's a plug and chug. So plug in 0.05 into this equation, and this equation. We're gonna check voltages.
Because if we're doing cosine with the radians and inside, our calculator needs to be in radians, doesn't it?
Or you need to, once you figure this out, do a conversion into degrees.
Okay.
Making sure it's running. Anybody have any of them yet?
I got no, never mind. I just mixed 2 of them together.
I got one of them, but my last 2 answers are negative.
That's okay.
Okay, so for the VC, I got 57.6978. For the VR, I got negative 109.596.
I got the same for VC.
All right.
And for the VPS, I got negative 52.447.
Those are looking good. Got a confirmation on any of them, besides the second one?
I have the same for the first one.
First one, all right. Confirmation on the last one?
Working on it. Yep. I got the same for
All
the
right.
last one.
So the question is, looking at that, is it right? I mean, is it at least consistent?
VC.
Should we be feeling good or wondering where our mistake is?
Seems close.
What'd you do?
I did the voltage of the power supply should equal the sum of the other two voltages.
Yep. And it looks like it's pretty darn close. At a crude level, the difference there is 52. This would be negative 52 if you add them together. We got negative 52 there.
Yeah. It's off by like half a volt, I think.
And considering the order of magnitude of, I'm okay with the 1% off.
I didn't listen to whatever you said about the volts, or I mean the time, I'm sorry. I went in and out.
You mean about whether it was right or not, or
Where you got time from?
I just made up a number.
Okay.
All I did here was just check for one specific time. Do the voltages work for one specific moment in time?
So you're saying whenever we come up with these equations, we can just come up with any time?
Yep.
To make sure that that's okay. Cause they should be, I guess they should grow the same as each other, in a sense.
In a sense, you say grow together, I mean, it's,
By
I mean, this one's negative and that one's positive, so, I mean, just so long as the sum of these two adds up to that.
Gotcha.
And you said to choose a time that's appropriate based on your radians per second.
Yeah, I mean, there's sometimes I'll do it of, when the power supply phasor is at 30 degrees, what are the voltages and currents? And so then that's just a matter of when is that equal to pi over 6?
Right.
But if I don't do that, you're just checking it, just pick a time that's on the order of magnitude of a period, or a fraction of a period.
Right.
Although there is nothing wrong with if you picked one, there's no reason why that shouldn't make it different, or why that would mess it up. But if you like t equal 1, then suddenly this is 377.585 versus 377. No, it's still, that shouldn't make a difference. I think I just picked the wrong number the other day and I'm just scarred by it.